In this video, I'll be discussing the complex conjugate and the absolute value of a complex number. First, we'll look at the complex conjugate. So let's begin by building our complex plane, and we'll add an arrow representing some complex number. And we'll assume that we can represent this number, which we denote by z, as re to the I theta in polar form or a plus bi in Cartesian form. Now let's remember what these numbers say about our arrow. The numbers a and b represent the horizontal and vertical lengths respectively. And the number r is the total length of this arrow, while theta is the amount that the arrow has been rotated. Now we want to look at the complex conjugate of this number. We're going to create a new arrow, and the way we get it is by reflecting this arrow representing z across the horizontal axis, like this. Now note that the arrow representing this new number still has total length r, and that the horizontal and vertical lengths are still a and b respectively. But now the angle of rotation is actually negative theta. The way we represent this new number, which is the complex conjugate, is via this. We call it z bar, and it's equal to re to the negative I theta, which is also equal to a minus bi. So let's actually define the complex conjugate. If we have a complex number z, which we assume has the polar form of re to the I theta or the Cartesian form of a plus bi, then the complex conjugate of z, which we denote by z with a bar on top, is defined to be re to the negative I theta, which is the polar form, or a minus bi in Cartesian form. Now let's do an example where we compute a complex conjugate. So assume our complex number is of the form 3 minus 2i. Well, for the complex conjugate, z bar is just going to be equal to, well, we just replace the i's with negative i's. So it's 3 minus 2 times negative I instead of positive I. And I'm going to pull the negative out, so we get 3 plus 2i. So the complex conjugate of 3 minus 2i is 3 plus 2i. So what's special about the complex conjugate of a number? We're going to look at what happens when we multiply a number by its complex conjugate. So let's assume we have some number, z, which is equal to re to the I theta. And as I write out what's happening algebraically, we're also going to visualize what's happening. So let's build a complex plane and an arrow, and I want this arrow to represent our number re to the I theta. So the angle should be theta, and the length should be r. What we'll do is multiply this number z by its complex conjugate and see what happens. Now its complex conjugate, z bar, is by definition just r e to the negative I theta. Now let's multiply them together. So we'll do z bar times z, which is equal to re to the negative I theta times r e to the I theta. And computing that out, we get r squared e to the I, then it's theta minus theta, which is just equal to r squared. Going back to our arrows, let's see what happens. So this part tells us that we need to rotate by negative theta, and then we need to multiply the lengths. So we stretch our arrow out, and we end up with an arrow of length r squared with no angle of rotation. The previous computation about multiplying a number by its complex conjugate leads us to the absolute value. So if we have a number, which we'll call z, and I'll assume its polar form is of the form re to the I theta, and its Cartesian form is a plus bi. Then its complex conjugate, which we denote by z bar, is given by re to the negative I theta, or a minus bi. Now we define the absolute value of z as follows. We write it as z with these bars around either side, and what it's equal to is the square root of z times z bar, which is what we previously computed. Now in polar form, we can represent it like this, and in Cartesian form, you may have seen this before, it's equal to the square root of a plus bi times a minus bi. Now remember, from the previous computation, we found out that z times z bar is equal to r squared. And since we're taking the square root, what we end up getting is that the absolute value is actually equal to just r. And what I want you to note is the following. The absolute value of z is just measuring the length of the arrow. Now let's do an example where we compute the absolute value. I'll do it in Cartesian form since I think it's pretty easy in polar form. So the number we'll choose is z, which is equal to 3 minus 2i. Then the complex conjugate, z bar, is equal to 3 plus 2i. Now let's compute the absolute value of z. So the absolute value of z, which by definition is the square root of z times z bar. And plugging things in, I get 3 minus 2i times 3 plus 2i. And I'm going to FOIL that out. And I get 9 plus 6i minus 6i minus 4i squared. The square root goes over all of it. Simplifying that, I get square root of 9. Then I have a plus 6i minus 6i, so that cancels, so I get a plus 0. And it's minus 4i squared. And remember, I squared is equal to negative 1. So I actually get a plus 4. So this is equal to the square root of 13, which is equal to the absolute value of z. And that's where I'm going to end this video.